In the grand cartography of the cosmos, there are places where the universe reveals its deepest architecture, not by the presence of light, but by the profound, unsettling absence of it. We map the heavens by the glittering pinpricks of galaxies, the swirling veils of nebulae, and the steady, familiar glow of stellar nurseries, crafting a narrative of a universe richly populated, energetically active, and fundamentally full. Yet, it is in the silent, dark expanses between these beacons that a more cryptic story is being written, a story that challenges our most fundamental understanding of cosmic structure and destiny. There exists, in the faint afterglow of creation and in the cold, modern surveys of the night sky, evidence of a peculiar kind of nothingness. This is not the simple, empty vacuum between stars, but a structured, colossal, and seemingly hungry emptiness, a void of such impossible scale and profound influence that it appears to be actively reshaping the cosmos around it. Astronomers, in their quiet, methodical probing of the dark, have come to know it as the Boötes Void, a spherical realm of near-nothingness, so vast it could swallow thousands of galaxies like our own without a trace, leaving behind only a chilling question: why is this region of space so desperately, unnaturally empty? And what force orchestrated this cosmic evacuation? To comprehend the true scale of this void, one must first step back from the concept of local emptiness. The space within our own galaxy is sparsely populated, with stars separated by light years of near-perfect vacuum. But this is a microscopic emptiness. On the larger scale of the cosmic web, the universe resembles a neural network of unfathomable complexity, with dense filaments of galaxy clusters and superclusters intersecting at luminous nodes, all woven together across billions of light years. The voids within this web are expected. They are the natural low-density troughs between the high-density peaks, like the deep valleys between mountain ranges. But the Boötes Void is not a valley. It is a chasm, discovered in the early 1980 seconds by astronomers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman during a survey of galaxy redshifts. Its nature emerged not from a direct image, for nothing is there to see, but from a stark deficit in the data. Where their maps of the universe in the direction of the constellation Boötes should have shown a gradual, textured distribution of galaxies, they instead found a staggering gap. Initial measurements suggested a spherical region approximately 250 million light-years in diameter, containing only a handful of galaxies where, based on the average density of the observable universe, there should be at least 10,000. Later, more refined observations have slightly tempered its scale and suggested a few more galactic inhabitants than first thought, but the essential mystery remains intact. This is a hole in the universe, a bubble of negation so large it defies straightforward explanation from the standard models of cosmic evolution. The emotional and scientific impact of such a discovery is best felt not in the numbers, but in a slow, contemplative exercise of scale. Imagine placing our Milky Way galaxy, a majestic spiral of hundreds of billions of stars, at the center of this void. From that solitary vantage point, if every star in our galaxy were extinguished to eliminate local light pollution, and if an observer possessed vision powerful enough to see distant galaxies, the view would be one of ultimate cosmic isolation. In every direction, for over 100 million light-years, the darkness would be nearly absolute. The few, faint galaxy clusters that do cling to existence within the void's interior would appear as the loneliest islands in the most expansive ocean imaginable. The great shining walls of the cosmic web that form the void's distant boundaries would be so far away that their light would be ancient, arriving from an era long before Earth itself had formed. For that imagined observer, the concept of a universe teeming with life and structure would feel like a distant myth, a story told by ancestors about a different reality altogether. This is the existential quality of the void. It is a place where the standard rules of cosmic density and community are suspended. A desert so extreme it prompts a deep, unsettling curiosity about what physical processes could possibly have left behind such a barrenscape. The investigation into such a void begins not with a presumption of a singular cataclysmic event, but with a slow, patient reconstruction of the cosmos's own formative processes. To understand why this particular region is so empty, we must listen to the faintest echo from the beginning of everything the cosmic microwave background radiation. This ubiquitous cold glow is the stretched and cooled remnant of the universe's fiery infancy, a snapshot of its structure when it was a mere 380,000 years old. In this ancient light, imprinted like a fossil in the sky, we see the seeds of all future structure, tiny quantum mechanical ripples in density that were amplified by gravity over eons. These infinitesimal fluctuations, hotter and colder spots in the early plasma, are the blueprints for the cosmic web. Where the primordial soup was slightly denser, gravity had more to work with, pulling matter inwards over billions of years to form galaxies, clusters, and the great filamentary walls. Conversely, the underdense regions, the cold spots in that early map, were destined to become the voids, as matter slowly drained away towards the gravitational pull of the denser regions surrounding them. In this standard model of cosmic evolution, known as the lambda-cold dark matter paradigm, voids are a natural and expected outcome. They are the expanding low-pressure troughs in the wake of the collapsing high-density peaks. But the Boötes Void presents a profound statistical tension. Its sheer size pushes against the predicted distribution of void sizes, generated by these random Gaussian initial conditions. It is an outlier, a Six Sigma event in a universe that, on the largest scales, is supposed to look roughly the same everywhere. This tension whispers of two possibilities. Either we have witnessed a statistical fluke of almost incomprehensible rarity, a cosmic lottery where the emptiest ticket was drawn, or our understanding of the initial conditions or the forces that shaped them is subtly, fundamentally incomplete. This leads us into the deeper, more shadowy realms of cosmological theory, where the void is not merely an absence, but potentially a signpost to invisible actors. The dominant narrative of our universe's composition is a humbling one. The ordinary matter that makes up stars, planets, and ourselves constitutes a mere 5% of the cosmic budget. Approximately 27% is the enigmatic substance known as dark matter, an invisible gravitational scaffold that holds galaxies together and guides the growth of the cosmic web. The remaining 68% is dark energy, the mysterious force driving the accelerated expansion of space itself. Within the vast interior of a void like Boötes, the dynamics of these dark components play out in a unique and revealing theater. With so little conventional matter to provide gravitational anchors, the behavior of dark matter and the influence of dark energy become magnified, their subtle effects more perceptible against the stark background of absence. The void is not static, it is evolving. As the universe expands, the underdensity of the void means the gravitational pull holding it together is weaker than in the surrounding matter-rich filaments. Consequently, dark energy, which acts as a kind of anti-gravity on cosmic scales, finds less resistance here. Theoretical models suggest that voids expand faster than the universe's average, their boundaries becoming sharper and more defined over time as they are effectively inflated from within by this dominant dark energy pressure. In this light, the Boötes Void is not just a relic of the past. It is an active participant in the future, a growing bubble of accelerated expansion, a microcosm of the ultimate fate of the entire universe if dark energy continues its dominion. It is eating the universe, not in a destructive, consuming sense, but in a quiet, relentless pushing apart of the very fabric of space within its domain, diluting any remaining traces of density towards a perfect, cold nothingness. But the intrigue of the void extends beyond its present dynamics. and into its potential connection to other cosmic anomalies, weaving a tapestry of mystery across different observational realms. One of the most persistent and debated enigmas in the cosmic microwave background is the so-called cold spot, a region in the southern galactic hemisphere that is significantly cooler than the average. For years, cosmologists have pondered its origin. Could it be a statistical fluke, an imprint of exotic physics from the universe's first, second, or perhaps a shadow cast by a foreground structure? A compelling, though controversial, hypothesis is that this cold spot is the integrated Sachs-Wolf effect of a supervoid, a vast, underdense region lying between us and the surface of last scattering. As CMB photons travel through the evolving gravitational landscape of the universe, they can gain or lose energy. Traversing a void that is becoming deeper due to dark energy's influence causes photons to lose a minuscule amount of energy, shifting them to a slightly cooler temperature. The hypothesized Eridanus supervoid, potentially aligned with the cold spot, would be a structure on a scale similar to Boötes. While the direct connection remains unproven and debated, the very suggestion ties the mystery of the CMB to the mystery of the large-scale voids. It posits that these immense nothingnesses are not just local curiosities. They are cosmic landscapes significant enough to leave an imprint on the very first light of creation, bending its journey across 14 billion years to whisper of the great emptinesses that lie in between. This creates a profound narrative link. The cold, ancient signal from the infant universe and the dark, modern map of galactic distribution may both be telling the same story of gravitational scarcity, a story where the voids are not passive backgrounds, but active sculptors of the cosmic narrative, their gravitational shadows stretching across time and space to touch the oldest light we can see. Within the profound quiet of the void, the few galaxies that do exist become objects of intense, almost anthropological study, for they are the survivors in a cosmic desert, and their forms tell a story of profound environmental influence. These isolated galaxies, often referred to as void galaxies, are not merely smaller or dimmer versions of their cousins in the dense clusters and filaments. They are fundamentally altered, living fossils of a different evolutionary path. In the rich environments of clusters, galaxies are subject to a brutal, transformative ecology. They are harassed by close encounters, stripped of their gas by the searing intracluster medium, and ultimately cannibalized in mergers, leading to the dominance of elliptical, red, and dead galaxies. But in the void, a galaxy experiences a life of solitude and scarcity. The primary evolutionary driver here is not interaction, but its absence. The pristine, low-density environment of a void means that these galaxies have largely been left alone since their formation, evolving in a state of quiet isolation over billions of years. This has profound consequences. They tend to be gas-rich, as there is no hot intergalactic medium to strip their reservoirs away. This abundance of cold gas fuels ongoing star formation, often resulting in irregular, bluish, and morphologically simple structures, frequently dwarf irregulars or low-surface brightness spirals. Their star formation histories are less frantic and more sustained, a slow-burning fuse compared to the starbursts and rapid quenching seen in denser environments. Studying these galaxies is like visiting isolated islands where unique evolutionary traits have developed away from the continental masses. They preserve a purer, less disturbed record of how galaxies form and grow when fed only by the meager, quiet accretion from their immediate surroundings. Yet, this very isolation presents a puzzle. In a region so devoid of raw material, how did these galaxies form in the first place? Their existence within the void suggests that the primordial density fluctuations, however faint, were still present in these regions, allowing these rare, lonely condensations of matter to coalesce against the gravitational odds, like single, stubborn flowers blooming in a vast and salted field. The profound emptiness also forces us to reconsider the very nature of cosmic nothingness. A void is not a perfect vacuum. It contains the ubiquitous cosmic microwave background radiation, a sparse mist of hydrogen and helium atoms, a conjectured web of dark matter, and the ever-present, repulsive energy of the vacuum itself, darkenergy. The dynamics within this near-nothing are governed by a delicate balance between opposing forces. While dark energy works to push the void's boundaries outward, accelerating its expansion, the gravitational pull of the slight overdensities in the surrounding filaments and walls acts as a containing sheath. Furthermore, the sparse baryonic matter within the void itself exerts a tiny inward gravitational tug. The interplay creates a complex flow field. Computer simulations of the cosmic web show that matter is not stationary within voids, but is in motion, streaming along subtle, dark matter-defined pathways towards the denser regions at the void's edges. This results in a phenomenon known as void evacuation, a slow, billion-year drainage of what little matter remains toward the gravitational wells of the surrounding structures. The void, therefore, is not born perfectly empty. It becomes emptier with time. The galaxies we see within it today may be the final, stranded remnants of this process. Systems that, due to their specific initial velocities and positions, avoided being swept up in the outflow. Some may even be on parabolic trajectories, destined to eventually leave the void entirely, drawn out by the gravitational pull of a distant filament. This paints the void not as a static whole, but as an active, flowing landscape, a basin whose rivers of matter all run outward, leaving behind an ever drier basin floor. The Boötes Void, in this interpretation, is a particularly efficient and ancient example of this evacuation process. A region where the drainage has been so thorough that it borders on the inexplicable, suggesting its initial density deficit was not just minor, but perhaps profoundly deep from the very beginning. This contemplation of initial conditions leads us to the most speculative and profound frontiers of cosmology, where the existence of a giant void challenges not just our models of evolution, but our fundamental picture of the universe's birth and its ultimate geometry. Could the Boötes Void be a signature of something beyond the standard inflationary paradigm? Inflation, the theory of a period of exponentially rapid expansion in the universe's first fraction of a second, was designed to explain the overall smoothness and flatness of the cosmos. It predicts a specific statistical distribution of density fluctuations, Gaussian and nearly scale invariant, that should not naturally produce voids of such extreme size and emptiness with any significant probability. The tension, while not yet a refutation, is a persistent whisper. Some theoretical cosmologists have explored more exotic early universe physics, such as models involving multiple interacting fields during inflation, or collisions between bubbles of space-time in a larger multiverse, which could imprint unusually large, underdense regions on the cosmic fabric. In such scenarios, the void might be a defect, a scar from a more violent and complex birth. Alternatively, the void scale forces us to confront the possibility of a universe whose global topology or curvature is not quite as we have measured from averaged observations. If the universe on the very largest scales is slightly open or possesses a complex, multiply-connected shape, such as a vast cosmic hall of mirrors, the apparent statistical anomaly of the void might be reconciled within that different geometrical framework. These are not mainstream explanations, but they are the kinds of ideas that extreme phenomena like the Boötes Void inevitably provoke. It serves as a gravitational lens, not bending light, but bending our theories, focusing intellectual effort on the most subtle and foundational assumptions we hold about the cosmos. It asks us whether our local, well-studied patch of the universe is truly representative, or if we are living in a modestly dense suburb on the edge of a continent that borders a silent, incomprehensible ocean of nothingness, an ocean whose very existence rewrites the map of all that is. The observational quest to understand a void is a fundamentally different endeavor from studying a brilliant quasar or a glittering galaxy cluster. It is an exercise in mapping absence, in defining a shape by the negative space that surrounds it. The primary tool for this is not a camera that collects light, but a spectrograph that measures redshift, the stretching of light from distant galaxies towards the red end of the spectrum due to the expansion of the universe. By conducting large systematic redshift surveys, such as the Sloan Digital Sky Survey, SDSS, or the more recent Dark Energy Spectroscopic Instrument, DESI survey, astronomers can construct three-dimensional maps of the cosmos. These maps do not show stars or nebulae. They show the positions of millions of galaxies, each a point of data in a vast statistical cloud. In such a map, the Boötes Void emerges not as an image, but as a spherical silence, a region where the points simply cease to exist. Refining our understanding of its true dimensions and internal structure is a painstaking process of filling in this negative space with ever more sensitive observations, searching for the faint, dwarf galaxies that may have been missed, and precisely charting the sharpness of its boundaries. This is how we measure the void's appetite, by counting the missing galaxies, by calculating the gravitational pull its absence exerts on the flows of surrounding matter, and by modeling the subtle ways its expansive growth distorts the paths of light from galaxies that lie behind it, a phenomenon known as weak gravitational lensing by underdensity. Each new, deeper survey scrutinizes this great emptiness, probing whether its terrifying scale is an artifact of incomplete data or a confirmed architectural feature of the cosmos. The data slowly confirms the latter. The void is real. Its dimensions are colossal, and its underdensity is profound. It stands as a testament to the fact that our most comprehensive maps of the universe are not just maps of where things are, but are equally, and perhaps more revealingly, maps of where things are not. This meticulous cartography of nothingness finds its ultimate purpose when it is woven into the broader quest to understand the dark components that govern cosmic evolution. Voids like Boötes are considered pristine laboratories for studying dark energy. In the dense, tangled knots of galaxy clusters, the gravitational interactions are complex and violent, masking the subtle background effect of dark energy's repulsive push. But in a void, where the gravitational pull of normal matter is negligible, the influence of dark energy is theoretically more dominant, and thus, its effects on the expansion rate of that local region should be more pronounced. By measuring the rate at which the void itself is expanding, a technique that involves studying the peculiar velocities of the few galaxies within it and the dynamics of its boundaries, cosmologists hope to place independent constraints on the properties of dark energy. Is it a constant vacuum energy, as Einstein's cosmological constant suggests? Or is it a dynamic field that has changed over time? The growth and evolution of giant voids offer a unique geometric test. Furthermore, the distribution of void sizes throughout the cosmos serves as a powerful statistical probe. The standard cosmological model, with its specific mix of dark matter, dark energy, and initial conditions, predicts a certain frequency of voids of different radii. A universe with more dark energy, or with different properties of the dark energy equation of state, would produce a different void size function. The Boötes Void, as an extreme outlier, is a critical data point in this distribution. Its very existence and the potential discovery of other supervoids helps cosmologists refine the parameters of their models, tightening the constraints on the nature of the dark universe. Thus, the void transforms from a cosmic curiosity into a precision instrument, its emptiness acting as a sensitive barometer for forces that are otherwise nearly imperceptible in the bustling, bright regions of space. Contemplating the future evolution of such a void leads to visions of cosmic destiny that are both serene and profoundly bleak. As the acceleration driven by dark energy continues to dominate the universe's dynamics, the expansion within voids will continue to outpace the global Hubble flow. The void will grow, not by acquiring new territory through force, but by the space within it stretching faster than the space in the denser regions around it. Its boundaries will become ever sharper, the density contrast between the void's interior and the surrounding filaments ever more extreme. The few remaining galaxies inside will find themselves on an island whose shores are receding at an ever-increasing rate. The galaxies on the void's outer edges will be redshifted into invisibility, their light stretched beyond detectability. For a hypothetical observer within the void in the far future, the surrounding cosmic web would have long since faded from view, leaving only a deepening, uniform darkness. The void, in its ultimate form, becomes a perfect realization of the de Sitter space predicted by cosmological constant dominated expansion, a featureless, eternally expanding vacuum. In this very long-term view, the Boötes Void is not an anomaly, but a harbinger. As dark energy continues its work, all of space will, on the largest scales, begin to resemble a void. Clusters and filaments will become isolated islands in an ever-widening sea of emptiness, their gravitational bonds eventually overcome by the relentless stretching of space. The great cosmic web will be pulled apart, its threads breaking until no new structure can form. In this distant epoch, the universe will be cold, dark, and empty, a fate often called the heat death or big freeze. The Boötes Void, then, offers us a premonitory glimpse of this final state. It is a pocket of the far future, embedded in the present, a region where the end of the story has already arrived, allowing us to study the mechanics of cosmic dissolution in real time. It is a quiet, expanding sphere of tomorrow, showing us that the universe is not just evolving toward complexity, but on the largest scales and over the longest time scales, is inevitably evolving toward a supreme and final simplicity. A simplicity defined by the absolute dominance of nothing over something, where the void is no longer an exception, but the rule. The human mind, when confronted with a phenomenon of such scale and silence as the Boötes Void, instinctively seeks not only scientific explanation, but also narrative and metaphor. For the void speaks to a deeper, almost philosophical disquiet. It represents the antithesis of our terrestrial experience, where matter is abundant, interactions are constant, and life thrives on complexity and connection. To gaze upon a map that highlights this great emptiness is to feel a chill of cosmic loneliness, a reminder that the universe is under no obligation to be welcoming, habitable, or even full. This existential resonance is perhaps why voids have captured the imagination beyond academic circles, appearing in works of science fiction as realms of forgotten civilizations, zones of broken physics, or as the haunting, literal nothingness that heroes must traverse. Yet, the scientific reality is more subtle and, in its own way, more profound. The void is not a place of broken laws, but a region where the laws of physics play out with stark, unadulterated clarity. It is a control experiment on a galactic scale. By studying the rare galaxies within it, we see galaxy evolution in its most undisturbed state. By measuring its dynamics, we isolate the effects of dark energy from the confounding noise of strong gravity. By mapping its shape, we trace the faintest ripples from the dawn of time. The void, therefore, is not merely an empty chapter in the story of the cosmos. It is a chapter written in a minimalist style, where every word, or in this case, every absent word carries immense weight and meaning. Its value lies precisely in its emptiness, for that emptiness provides the silent background against which the symphony of cosmic structure can be truly understood. In a universe that often feels overwhelmingly bright and crowded in our telescopic imagery, the void reminds us that the dominant experience of space, on the grandest scales, is one of profound and growing isolation, a slow, cold whisper of a fate that is written not in fire, but in the relentless, patient geometry of expansion. Our journey through the concept of this cosmic void inevitably brings us back to our own place within the vast architecture we are attempting to chart. We do not reside in a void. Our Milky Way galaxy is part of the Laniakea supercluster, a massive filamentary structure hundreds of millions of light-years across. We are embedded in a region of average density, a cosmic suburb. This is fortunate for our existence, as the dense environments of galaxy clusters are often too violent for stable planetary systems, and the profound scarcity of voids likely could not have provided the heavy elements necessary for life in any abundance. Our position, however, may bias our perception. Just as an island dweller might initially struggle to comprehend the depth of a continental desert, our location within a filament of the cosmic web may make a structure like the Boötes Void appear more anomalous than it truly is in the global census of the universe. This is a central challenge of cosmology. We have but one universe to observe, and we are observing it from a single, potentially special point within it. Could it be that we are situated on the edge of a much larger underdensity, a vast, gentle trough that makes the great voids appear more extreme from our vantage point? Some cosmologists have proposed the idea of a local hole or a Hubble bubble, a region hundreds of millions of light-years in diameter, where the average density is slightly lower than the cosmic mean, which could affect our local measurements of the Hubble constant. While controversial and far from confirmed, such ideas highlight the humbling fact that our entire observable universe, a sphere nearly 100 billion light-years across centered on Earth, is still just a single sample. The Boötes Void, for all its majesty, is a feature within that sample. Its ultimate meaning may only become clear when we can conceive of a truly external, God's eye view of cosmic structure, a perspective forever denied to us by the finite speed of light and the horizon of our observable bubble. We are left to piece together the full tapestry from the view within the loom, aware that the most startling patterns may only emerge from the careful, patient study of both the threads and the spaces between them. As we reach the concluding contemplation of the void that is eating the universe, we find that its story is one of beautiful, terrifying symmetry. It is a story that begins in the quantum whisper of the first instant and ends in the eternal silence of the last. The void is a product of the universe's initial conditions, a fossil of its inflationary birth. It is shaped by the invisible hand of dark matter, which sketched the gravitational potential wells from which matter fled. It is now being inflated by the mysterious pressure of dark energy, its emptiness serving as the medium through which this dominant force expresses its clearest signature. And it points toward a future where this same force will homogenize all of creation, turning the entire observable universe into a void of a different kind, a cold, isotropic, and lifeless expanse, where no new stories will be written. The Boötes Void is thus a microcosm of the entire cosmic narrative: genesis, structure, and dissolution. It teaches us that creation and emptiness are not opposites, but partners in a dynamic billion-year dance. The luminous structures we cherish, the stars, the galaxies, the nebulae, are the fleeting, brilliant exceptions. The enduring reality, the final and lasting state of the cosmos, appears to be one of vast, quiet nothingness. To study the void, then, is to study the ultimate fate of everything we see. It is to look into a dark mirror that reflects not our present, but our distant future. It asks us to find meaning, not only in the light and the heat and the vibrant chaos of creation, but also in the slow, cold, and majestic expansion of the dark. In its silent, growing sphere, we find a profound scientific truth that in the grand calculus of the universe, the nothingness is not merely background. It is an active, shaping, and ultimately dominant character in the story of all that is, all that was, and all that ever will be. Yet, the narrative of the void does not end with a passive contemplation of its inevitable expansion. It also compels us to consider the active, ongoing detective work that seeks to uncover its true origin story a search that leads astronomers to scrutinize the void, not for what it contains, but for the subtle imprints its growth leaves on the fabric of space-time itself. One of the most promising avenues for this investigation lies in the study of the integrated Sachs-Wolf effect and its cross-correlation with the large-scale structure. As previously mentioned, photons from the cosmic microwave background traversing an evolving gravitational potential, like that of a growing void, gain or lose energy. This creates a specific, statistically detectable signature, a subtle, ring-like pattern of temperature variations around the void's projected location in the CMB sky. Finding such a correlation between the positions of known supervoids and specific cold spots in the microwave background would be a direct observational link between the universe's ancient light and its modern structure, offering a powerful confirmation of the role of dark energy in shaping these empty regions. The search for this signal is extraordinarily difficult. Buried beneath the noise of the primordial CMB fluctuations and foreground galactic emissions, but it represents a direct test of whether the void's emptiness is indeed being actively deepened by the repulsive force that governs cosmic acceleration. A confirmed detection would transform the void from a static curiosity into a dynamic laboratory, its very emptiness serving as a calibrated instrument that records the work of dark energy across billions of years. The Boötes Void, given its size and prominence, is a prime target for such studies, a dark lens through which we might finally bring the ephemeral nature of dark energy into sharper, more tangible focus. Simultaneously, the frontier of void cosmology is being pushed forward by a new generation of massive spectroscopic surveys that are mapping the universe in 3 dimensions with unprecedented depth and breadth. Instruments like the Dark Energy Spectroscopic Instrument, DESI, and the future Euclid Space Telescope, and Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, are not merely adding more points to the map. They are revealing the finer texture of the cosmic web, including the intricate substructure within voids themselves. It was once thought that voids were simple, roughly spherical, and featureless. Modern simulations and now observational hints suggest a more complex interior ecology. Voids may contain their own faint web of dark matter filaments, along which the few resident galaxies are aligned. They may harbor even smaller subvoids within them, a hierarchy of emptiness like bubbles within bubbles. The distribution and motions of the galaxies inside the Boötes Void, as these new surveys finally collect enough of these rare objects for statistical analysis, will tell us about the dynamics of this internal landscape. Are the galaxies streaming along preferred directions, tracing the ghostly filaments of a dark matter skeleton that failed to collect much luminous matter? Do they show signs of peculiar velocities that indicate the void's interior is not uniformly expanding, but is shaped by residual gravitational tugs from unseen density variations? The answers will refine our models of how structure forms and fails to form in the most underdense regions. Each faint galaxy discovered within the void's confines is a precious data point, a tracer particle, in a vast, dark fluid dynamics experiment, helping us to understand the hydrodynamics of an ocean, where the water is mostly missing and the currents are defined by absence. This brings us to a final, resonant thought regarding our relationship with these great cosmic nothings. In a fundamental sense, the existence of the Boötes Void is a testament to the power of human curiosity and our capacity to see the universe not just for what shines, but for what does not. For most of human history, the darkness between the stars was merely a backdrop, an empty canvas. It took the development of modern cosmology, redshift surveys, and the conceptual framework of the cosmic web to recognize that certain patches of darkness are not passive backdrops, but active, evolving entities with their own physics, history, and future. We have learned to measure the shape of nothing. We have developed the mathematics to describe its growth. We have built telescopes capable of sensing the faintest glimmers within it, not to celebrate the light, but to better define the dimensions of the dark that surrounds them. The void, therefore, is a triumph of scientific perception. It represents an expansion of our consciousness into realms where traditional markers of significance, light, heat, density, are absent. It challenges us to find meaning in subtraction, in negative space, in the slow, grand rhythms of dissolution and expansion. The void that is eating the universe is more than a dramatic title. It is a precise description of an ongoing physical process that we have been able to identify, name, and study. In doing so, we have not only uncovered a mysterious feature of the cosmos, but have also demonstrated the remarkable adaptability of the human intellect. Its ability to peer into the abyss and not only see nothing, but to see the profound and intricate, something that the nothingness itself represents. A something made of initial conditions, gravitational potentials, dark energy, and the relentless flow of time. It is in this silent, expanding sphere that we may ultimately find some of the loudest clues to the deepest secrets of the universe, a place where the absence of everything we know becomes the key to understanding everything we do not. The philosophical implications of the void extend beyond cosmology, touching upon our very understanding of existence and the nature of physical reality. In a universe dominated by dark energy, the ultimate fate is not a cataclysm of collapse, but a slow, asymptotic fade into darkness and isolation. The Boötes Void serves as a localized, present-day model of this future. Its immense scale and profound emptiness force a confrontation with the concept of nothing as a physical state. Is the void truly nothing? Or is it a specific, rich configuration of fields and energies that our language and intuition simply label as absence? Within its bounds, the quantum vacuum still seethes with virtual particle pairs popping in and out of existence. Dark energy exerts its constant negative pressure, and the faintest gravitational waves from ancient cosmic events may still propagate. This nothing is, in fact, a complex and physically active medium, just one that is devoid of the condensed, luminous matter that our senses and instruments are primarily tuned to detect. The void, therefore, challenges the Aristotelian notion that nature abhors a vacuum. Modern cosmology suggests that on the largest scales, the universe not only tolerates a vacuum, but is actively and increasingly becoming one. The void is not an anomaly to be filled. It is the default state toward which all things are evolving. This inversion of intuition is one of the most profound lessons of modern astrophysics. The vibrant, structured, and star-filled universe of our current epoch is a temporary, albeit long-lived, phase in a much grander timeline, a brilliant but fleeting bloom in a field that will eventually return to a state of quiet, uniform potential. Observing the Boötes Void is like watching the field begin to reclaim the garden, a process so slow and vast it is almost geological in its cosmic pacing, reminding us that the engines of creation have a reverse gear and it is engaged. This contemplation naturally leads us to consider the possibility of life within such an environment, a thought experiment that stretches the concept of habitability to its limits. A civilization evolving on a planet orbiting one of the rare, isolated stars within the void would inherit a profoundly different cosmological perspective. Their night sky, devoid of the magnificent bands of distant galaxies and the dense star fields that grace our own Milky Way, would be a much darker and emptier canvas. The few neighboring galaxies in their void would be faint, distant smudges. The concept of a universe teeming with galaxies would be, for them, a theoretical construct deduced from the redshift of those few distant specks and the subtle whispers of the cosmic microwave background, rather than an observable fact. Their cosmic isolation would be absolute, raising profound questions about the development of science and philosophy in such an environment. Would they ever conceive of the Big Bang, the cosmic web, or dark energy without the obvious visual evidence of large-scale structure that we take for granted. Their greatest astronomical discoveries might center on the mysteries of the void itself, the peculiar motions of their own galaxy, the puzzling lack of neighbors, the strange cold spot in their CMB. For them, the void would not be a mysterious anomaly. It would be the universe, their entire lived experience of cosmic space. This inversion of perspective is a crucial exercise in cosmological humility. It underscores that our scientific narratives are deeply shaped by our location within the cosmic web. We have built a cosmology from a vantage point of relative density. A void dweller's cosmology would be built from a vantage point of profound scarcity. And while the underlying physical laws would be the same, the path to discovering them and the emphasis of their study would be radically different. The Boötes Void, therefore, stands as a monument to cosmic variance, a reminder that the universe offers a spectrum of possible homes, from the bustling galactic metropolises to the silent, dark deserts, and that the view of the cosmos from each is a unique and partial portrait of the whole. As we integrate the existence of such colossal voids into our standard model of cosmology, we are forced to refine our simulations and theories to account for these extreme outliers. The lambda-cold dark matter model, for all its spectacular successes, is continually stress-tested by observations like the Boötes Void. While it can produce large voids in simulations, the frequency and scale of the very largest ones, like Boötes, remain at the edge of statistical plausibility. This tension is not a crisis, but a catalyst. It drives cosmologists to run ever larger, more detailed n-body simulations of cosmic structure formation, involving trillions of dark matter particles in boxes billions of light years on a side, to see if such a void is a once-in-a-universe fluke or a more common feature than previously thought. It also prompts investigations into the nature of the initial power spectrum of density fluctuations. Were there rare, large-amplitude negative fluctuations in the early universe that could have seeded these supervoids? Or could alternative models of dark matter, such as warm or interacting dark matter, which suppress small-scale structure, lead to a different distribution of void sizes? The void thus acts as a probe of physics at both extremes: the highest energies of the inflationary epoch that set the initial conditions, and the lowest energy, longest timescale effects of dark energy that govern its present evolution. It is a bridge between the universe's first instant and its final state, a single feature interrogating the entirety of the cosmological model. Each new, deeper survey that maps more of the void's interior and boundaries, each refined measurement of its gravitational effects, provides another data point to constrain these grand theories. The silent void, in its immense passivity, is an active participant in the scientific process, its emptiness posing questions that echo through the halls of theoretical physics, demanding answers that are as precise and profound as the phenomenon itself. In the quiet, expansive narrative of the cosmos, the Boötes Void also serves as a crucial calibrator for one of the most contentious measurements in modern cosmology, the Hubble constant, which quantifies the current rate of the universe's expansion. Different methods for measuring this constant using the cosmic microwave background as a pristine early universe relic versus using supernovae and other standard candles in the local universe have stubbornly refused to align, a discrepancy known as the Hubble tension. The peculiar dynamics within and around a giant void may offer a potential, though partial, resolution to this puzzle. If our local galactic neighborhood, including the Milky Way, were situated on the slope of an immense underdensity far larger than the Boötes Void itself, a vast local bubble, the gravitational effects of this surrounding emptiness could subtly alter the apparent velocities of nearby galaxies used to calibrate the local expansion rate. In simpler terms, we might be living in a region where space is expanding slightly faster than the true global average because we are inside a gentle, giant, void-like structure. The outflow of matter from the void center, a residual velocity imparted by the gravitational pull of the surrounding denser regions, could add a small but systematic component to the recession velocities we measure for galaxies, making the local universe appear to be expanding more quickly. While the Boötes Void itself is too distant to directly cause this effect on our local measurements, its existence proves that such vast underdensities are part of the cosmic fabric. If a larger, subtler version envelops our own position, it could be biasing our local Hubble constant measurement upward. Studying the detailed velocity flows in and around the Boötes Void provides a template for understanding this very phenomenon. It is a laboratory for measuring how underdensities warp the local flow of the cosmic expansion. Thus, the void's relevance extends beyond its own mysteries. It becomes a Rosetta Stone for interpreting potential anomalies in our own cosmic backyard. Its stark emptiness, helping to decode a subtle signal that might explain a foundational disagreement at the heart of cosmology. Beyond the realm of pure cosmology, the void also presents an unparalleled environment for studying the interstellar and intergalactic medium in its most rarefied state. The space between galaxies, even in clusters, is not empty. It is filled with a hot, diffuse plasma known as the intracluster medium. But within a void, this medium is expected to be cooler, less dense, and more pristine, largely unenriched by the heavy elements, forged in generations of stars, and scattered by supernovae and galactic winds. Probing this tenuous material is extraordinarily difficult, as it emits very little light. However, astronomers can use it as a backdrop. When the light from a distant quasar or bright galaxy passes through the void, the sparse atoms within the void's interior will imprint extremely weak absorption lines on that light's spectrum. These lines, primarily from neutral hydrogen, the Lyman alpha forest, are like forensic fingerprints of the void's content. By studying these ultra-faint absorption features in the light of background sources that serendipitously lie behind the Boötes Void, researchers can measure the temperature, density, and metallicity of the gas within this great emptiness. Is it truly primordial, a pocket of hydrogen and helium, nearly unchanged since the universe's first few minutes? Or does it contain trace signatures of ancient early stellar generations from the void's few galaxies, a faint pollution spread over billions of years? The answers would tell us about the efficiency of feedback processes, the ways galaxies inject energy and metals into their surroundings in the most extreme low-density environments. The void, in this context, becomes a vast diffusion chamber, where any enrichment event is diluted across such a colossal volume that its signature becomes a whisper requiring exquisitely sensitive instruments to detect. This painstaking work turns the void into a cosmic chemistry lab, where the experiments are performed by nature across million light-year scales, and the data is read in the distorted spectra of impossibly distant quasars. The emotional and aesthetic resonance of the void cannot be separated from its scientific impact, for it taps into a deep-seated human response to the sublime, the mixture of awe, wonder, and terror evoked by phenomena of overwhelming scale and power. The glittering starfields of the Milky Way inspire one kind of wonder. The vast, structured emptiness of the Boötes Void inspires another, more contemplative and daunting variety. It is the difference between marveling at a magnificent, ancient forest and standing at the edge of a silent, boundless desert under a night sky devoid of landmarks. Both are beautiful, but the latter's beauty is austere, demanding a shift in perception. In an age where our digital lives are increasingly saturated with information, noise, and visual stimulation, the void represents the ultimate antithesis, a concept of pure negative space, of silence, of minimalism pushed to a cosmic extreme. It serves as a metaphor for isolation, for the unknown, for the parts of any map that are still labeled terra incognita. For the scientist, it is a puzzle of absence. For the philosopher, it is a meditation on nothingness. For the storyteller, It is a setting of profound potential. This multifaceted resonance ensures that the void will continue to captivate long after its specific cosmological parameters are precisely measured and comfortably nestled within an updated theoretical model. It has transcended its status as a mere astronomical object to become a cultural and intellectual touchstone, a symbol of the ultimate frontiers of both space and human understanding. Its very existence in our scientific canon is a testament to our ability to push inquiry into realms where the traditional objects of study vanish, leaving only the subtle, haunting geometry of space itself as the subject of our relentless, quiet curiosity. The story of the Boötes Void, and of cosmic voids in general, is inextricably linked to the evolving technology of observation, a narrative of seeing by not seeing. The initial discovery in the 1,980 seconds was made possible by pioneering redshift surveys that used photographic plates and early digital detectors, painstakingly measuring the spectra of galaxies one by one. The void revealed itself as a startling gap in the data, a blank column in a ledger of cosmic addresses. Today, the investigation continues with robotic telescopes that can autonomously target thousands of galaxies a night, fiber optic spectrographs that capture the light of hundreds simultaneously, and space observatories that scan the sky in wavelengths invisible from Earth. This technological evolution is slowly filling in the negative space, not by finding the expected throngs of galaxies, but by confirming the void's true, austere geography and discovering its faintest inhabitants. Each new instrument, with its greater sensitivity and wider field of view, allows us to probe deeper into the void's heart, to find the dimmest dwarf galaxies that previous surveys missed, and to map the tenuous gas that constitutes its true, diffuse contents. This incremental progress is a different kind of exploration than the dramatic, close-up imaging of a planetary surface. It is a statistical, cumulative unveiling, a gradual sharpening of the boundaries of a shadow. The Jameswebb Space Telescope, with its unprecedented infrared sensitivity, could play a surprising role here. While not a wide-field survey instrument, its powerful spectrographs might be trained on the rare, faint galaxies within the void to study their stellar populations and chemical compositions in exquisite detail, revealing their isolated, evolutionary history. Similarly, radio telescopes like the upcoming Square Kilometre Array will map the neutral hydrogen gas throughout the cosmos with such sensitivity that they could detect the faintest wisps of gas within voids, tracing the dark matter scaffolding directly. The void, therefore, is a moving target for science. As our vision improves, its nature comes into ever sharper focus, not as a place of mere emptiness, but as a complex region defined by extremely low-density physics, a frontier that recedes before our advancing technological grasp, always promising deeper secrets to those who learn to look at the dark in the right way. This technological march also allows us to search for other, perhaps even more extreme voids, to see if Boötes is truly unique or merely the first of its kind that we stumbled upon. The statistics of void sizes are a powerful cosmological probe, and finding the largest possible void sets an upper bound on the initial conditions of the universe. Recent large-scale surveys have indeed cataloged other supervoids, though few rival Boötes in its combination of sheer size and profound emptiness. The KBC void, or local hole, is a hypothesized underdensity of even larger scale but much milder density contrast, potentially encompassing our own position. The Eridana supervoid remains a candidate explanation for the CMB cold spot. Each newly discovered void adds a data point to the distribution, helping cosmologists refine their models. Could there be a void so large that it challenges the cosmological principle itself? The assumption that the universe is homogeneous and isotropic on sufficiently large scales? The continued search is not just about cataloging emptiness. It is a test of one of the foundational pillars of modern cosmology. If we found a void that spanned a significant fraction of the observable universe, it would force a radical reconsideration of our place within the cosmic whole. The ongoing mapping of the dark patches in the cosmic web is, in this sense, a fundamental audit of the universe's structure, a check to ensure that the smoothness we infer from the CMB is truly manifest in the distribution of galaxies. The Boötes Void sits at the edge of acceptability within the current paradigm. Finding something larger or emptier would push that paradigm to its breaking point, making the study of these nothings one of the most potentially revolutionary fields in observational cosmology. Ultimately, the enduring mystery of the Boötes Void brings us full circle, back to the human experience of the cosmos. Before the advent of modern science, the darkness between the stars was a canvas for mythology, a realm of gods, spirits, and ancestral beings. It was both a source of fear and a source of wonder. The scientific revolution replaced those myths with a universe of physical laws, but it did not eliminate the wonder. It transformed it.
The Boötes Void represents this transformed wonder perfectly. It is a phenomenon that is understood in terms of Gaussian random fields, the integrated Sachs-Wolf effect, and dark energy equations of state. Yet it retains a profound capacity to evoke a sense of the sublime. It is a reminder that the universe is not obligated to conform to our aesthetic or emotional desires for symmetry, abundance, or neighborliness. It can produce, through the blind workings of physics stretched across billions of years, regions of breathtaking, almost terrifying emptiness. To acknowledge this, to study it, and to incorporate it into our understanding is to achieve a more mature, more complete relationship with the cosmos. We learn that the universe is not just a collection of beautiful objects, but also a dynamic landscape of relationships between presence and absence, density and scarcity, creation and dissipation. The void is the counterpoint to the galaxy, the silence between the notes that makes the music possible. In learning to appreciate the void, we learn to appreciate the full spectrum of cosmic reality, from the brilliant, frenetic centers of galaxy clusters to the vast, still, and expanding spheres where almost nothing happens at all, and where the slow, patient work of dark energy is writing the final, quiet chapter of universal history in the geometry of empty space. In the final synthesis, the narrative of the void that is eating the universe resolves not with a definitive answer, but with a deepened appreciation for the evolving, multi-layered dialogue between human inquiry and the cosmos. The Boötes Void is no longer merely an anomaly. It has become a standard against which we measure our theories, an extreme environment that tests the limits of our simulations, and a philosophical concept that expands our perception of what constitutes a meaningful feature in the grand architecture of existence. Its study exemplifies the scientific method at its most ambitious, beginning with the shock of an unexpected absence, proceeding through decades of meticulous observation and theoretical modeling, and culminating in the integration of that absence into a richer, more nuanced understanding of the whole. The void has been digested by cosmology, but in the process, it has subtly altered the body of knowledge that consumed it, leaving cosmology itself changed, more attentive to the power of negative spaces and the long-term dynamics of decay and expansion. The mystery has not been solved so much as it has been refined, transformed from a blunt, "Why is there nothing there?" into a suite of precise, quantitative questions about initial power spectra, dark energy equations of state, velocity flows, and gas phase metallicity in near vacuum conditions. This transformation is the true mark of scientific progress, not the elimination of wonder, but its channeling into ever more productive and profound lines of inquiry. As we project forward, the role of such voids in the future of cosmology is assured. They will be used as standard rulers. The Alcock-Pazinski test, which uses the apparent shape of spherical objects like voids to measure the geometry of the universe, relies on these vast empty regions as ideal, naturally occurring spheres. By measuring how much the void appears distorted along the line of sight compared to its transverse dimensions, cosmologists can extract information about the expansion history and the nature of dark energy. The Boötes Void, and others like it, will thus become geometric tools, their emptiness providing a clean, large-scale shape against which the stretching of spacetime can be measured. Furthermore, the correlation between voids and the weak gravitational lensing of the distant cosmic microwave background and galaxy fields will provide a unique gravitational tomography, mapping the distribution of all matter, luminous and dark, across these vast basins. In the coming era of precision cosmology, voids will transition from being exotic subjects of study to being foundational components of the observational toolkit. Their very lack of content makes them pristine windows, free from the complicated astrophysics of stars and gas, offering a direct view of the underlying dark matter skeleton and the imprint of darkenergy's work. The void, therefore, finds its ultimate purpose not as an endpoint of curiosity, but as a means to a deeper end, a key to unlocking the parameters of the cosmic destiny it so starkly prefigures. And so we return to the image that began this contemplation, a sphere of silence, hundreds of millions of light years wide, slowly growing larger and emptier in the eternal night. It is a structure defined by loss, by the drainage of matter, by the victory of expansion over attraction. Yet, in the precise, patient light of science, it is also a structure of immense generative power. It generates new questions, new tests for our theories, new methods for observation, and new perspectives on our place in the cosmos. It reminds us that the universe is a story of opposing tensions, between gravity and expansion, between concentration and dissipation, between the brilliant, fleeting fires of creation and the cold, enduring darkness that will eventually encompass them all. The Boötes Void is a single, profound sentence in that story, written in the language of geometry and dynamics rather than words. It tells us that the cosmos is capable of scales of emptiness that dwarf human imagination, and that within that emptiness, the fundamental forces of nature play out their long game with pristine, unobscured clarity. To listen to the void is to listen to the universe itself, stripped of its ornamentation, speaking in the slow, deep tones of spacetime curvature and quantum fields. It is a whisper from the future, a report from the frontier of dissolution, and a permanent testament to the fact that in the cosmic ledger, nothingness is not a zero, but a number of profound and evolving significance, a dynamic state that holds the keys to understanding everything from the first microsecond to the last star.